And the last example is actually such a huge, beautiful example. It brought me to tears the first time I saw it, because I personally think it's so cool that, have you guys know a little bit about proteins and functions? The last example for today, it's one of the most amazing examples I think of. So the protein structure, it often determines the function that protein can have. So let's talk a bit about coronavirus. So I think that our understanding of nature will be fundamentally changed since we have an advancement in artificial intelligence. So one of the reasons coronavirus was spread so easily is since the protein over the vesicle itself on the spike protein could bind to the receptors on our host membranes and our nose receptors. Coronavirus can affect all sorts of animals. The 3D structure is very dynamic, as I said, and the functions that a cell can perform can change. So if we know the 3D shape of a protein, we can figure out its function and then design therapies that way. We can understand how this protein is involved in the cell, what diseases it could be involved in, what are drugs or therapies that we can use to target that protein in various diseases. But how do we determine this structure? So if we had to figure out the structure of one protein by itself, it would take us longer than the known age of the universe. If I had to try out and figure out the structure of a protein, it would take me 10 to the 300th power, which is insane. It would take me longer than the age of the universe. We have millions of proteins out there in our cell and our body. We can spend a lot of time, energy, and money conducting lab experiments to figure it out. So it could take a huge, long time. So what if I said that AI can help us predict the protein structure really accurately within days? So we can sequence DNA now. Before it used to be $3 billion, and now it's under $1,000. And we can know these amino acid sequences more reliably. So otherwise, before, to determine a protein structure, we would need to create a protein crystal or do X-ray diffraction. It'd be very, very difficult. And this is a very, very long and unsolved problem. There are about millions and millions of proteins out there, and we only know the shape of maybe 170,000. So we could use computational simulations, experiments, but it's so expensive and time consuming. And this is a problem that the biologists thought would take us, maybe our grandchildren would figure this problem out. It would take us another 50 years or so. But this is a problem that we can solve using AI. We can use AI to predict the 3D shape of proteins. We can take a protein sequence and then do two calculations. One is a distance prediction, and the other is an angle prediction. So we know so for the proteins that we know their shape, we can try to make predictions about it and then see how far away we are from the truth and then make adjustments to our neural network till we can be more accurate. So that's exactly how this worked. So this is how they take a sequence and then try to predict the 3D structure using these neural networks, deep learning we'll talk about tomorrow. So I'll end on this video for you guys. And this video is so cool. Like, I got really emotional when I saw this for the first time because it's so amazing what this can do. Solved a problem like 50 years before we thought it could ever be solved using AI.
Covered more about the world than any other civilization before us. But we have been stuck on this one problem. How do proteins fold up? How do proteins go from a string of amino acids to a compact shape that acts as a machine and drives life?
When you find out about proteins, it is very exciting.
You could think of them as little biological nanomachines.
They are essentially the fundamental building blocks that power everything living on this planet.
If we can reliably predict protein structures using AI, that could change the way we understand the natural world.
Protein folding is one of these holy grail type problems in biology. We've always hypothesized that AI should be helpful to make these kinds of big scientific breakthroughs more quickly.
And then I'll probably be looking at little tunings that might make a difference.
You should be creating histogram 1 and a background histogram.
We've been working on our system AlphaFold really hard now for over 2 years. Rather than having to do painstaking experiments, in the future biologists might be able to instead rely on AI methods to directly predict structures quickly and efficiently.
Generally speaking, biologists tend to be quite skeptical of computational work, and I think that skepticism is healthy and I respect it, but I feel very excited about what AlphaFold can achieve.
CASP is when we say, look, DeepMind is doing protein folding, this is how good we are, and maybe it's better than everybody else, maybe it isn't.
We decided to enter CASP competition because it represented the Olympics of protein folding.
CASP, we started to try and speed up the solution to the protein folding problem. When we started CASP in 1994, I certainly was naive about how hard this was going to be.
It was very cumbersome to do that because it took a long time.
Let's see what are we doing still to improve.
Typically 100 different groups from around the world participate in CASP, and we take a set of 100 proteins and we ask the groups to send us what they think the structures look like.
We can reach 57.9 GDT on CASP-12 ground truth. CASP has a metric on which you will be scored, which is this GDT metric.
On a scale of 0 to 100, you would expect a GDT over 90 to be a solution to the problem.
If we do achieve this, this has incredible medical relevance.
The implications are immense, from how diseases progress, how you can discover new drugs. It's endless.
I wanted to make a really simple system, and the results have been surprisingly good.
The team got some results with a new technique. Not only is it more accurate, but it's much faster than the old system.
I think we'll substantially exceed what we're doing right now.
Well, then it's a game changer, I think.
In CASP 13, something very significant had happened. For the first time, we saw the effective application of artificial intelligence.
We've advanced the state of the art in the field, so that's fantastic, but we've still got a long way to go before we've solved it.
The shapes were now approximately correct for many of the proteins, but the details, exactly where each atom sits, which is really what one would call a solution, were not yet there.
It doesn't help if you have the tallest ladder when you're going to the moon.
We hit a little bit of a brick wall since we won CASP. Then it was back to the drawing board and like, what are our new ideas? And then it's taken a little while, I would say, for them to get back to where they were, but with the new ideas. And then now I think we're seeing the benefits of the new ideas. They can go further, right? So that's a really important moment. We've seen that moment so many times now. But I know what that means now, and I know this is the time now to press. We need to double down and go as fast as possible from here. I think we've got no time to lose.
So the intention is to enter CASP again. CASP is deeply stressful.
There's something weird going on with the learning, because it is learning something that's correlated with GDT, but it's not calibrated.
I feel slightly uncomfortable. We should be learning this, in the blink of an eye. The technology advancing outside DeepMind is also doing incredible work.
And there's always the possibility another team has come somewhere out of left field that we don't even know about.
Someone asked me, well, should we panic now? Of course, we should have been panicking before.
It does seem to do better, but still doesn't do quite as well as the best model. So it looks like there's room for improvement.
There's always a risk that you've missed something, and that's why blind assessments like CASP are so important to validate whether our results are real. Obviously, I'm excited to see how CASP 14 goes.
My expectation is we get our heads down, we focus on the full goal, which is to solve the whole problem.
The Prime Minister has announced the most drastic limits to our lives that the UK has ever seen in living memory.
I must give the British people a very simple instruction. You must stay at home.
We were prepared for CASP to start on April 15th because that's when it was originally scheduled to start, and it's been delayed by a month due to coronavirus. I really miss everyone.
I struggled a little bit just kind of getting into a routine, especially with my wife. She came down with the virus.
Oh.
I mean, luckily it didn't turn out too serious.
CASP started on Monday.
Can I just check this diagram you've got here, John? This one where we ask ground truth. Is this one we've done badly on?
We're actually quite good on this region. If you imagine that we hadn't have said it came around this way, but had put it in
down
right
instead.
spot.
Yeah.
One of the hardest proteins we've gotten in CASP thus far is a SARS-CoV-2 protein
Not part of the coronavirus, COVID-19.
called ORF8.
ORF8 is a coronavirus protein. We tried really hard to improve our prediction, like really, really hard. Probably the most time that we have ever spent on a single target.
So we're about 2/3 of the way through CASP, And we've gotten 3 answers back.
We now have a ground truth for ALP8, which is one of the coronavirus proteins. And it turns out we did really well in predicting that.
Amazing job, everyone, the whole team. It's been an incredible effort.
Here what we saw in Cas14 was a group delivering atomic accuracy off the bat, essentially solving what in our world is 2 problems. How do you look to find the right solution, and then how do you recognize you've got the right solution when you're there?
All right, are we mostly here? I'm going to read an email. I got this from John Malt. I'll just read it. It says, John, as I expect you know, your group has performed amazingly well in Cas14, both relative to other groups and in absolute model accuracy. Congratulations on this work. It is really outstanding.
AlphaFold represents a huge leap forward that I hope will really accelerate drug discovery and help us to better understand disease. It's pretty mind-blowing.
You know, these results were, for me, having worked on this problem so long, after many, many stops and starts, and will this ever get there? Suddenly, this is a solution. We'd solved the problem. This gives you such excitement about the way science works, about how you can never see exactly or even approximately what's going to happen next. There are always these surprises, and that really, as a scientist, is what keeps you going. What's going to be the next surprise?
So how did you guys feel about that? Did any of you guys get goosebumps? Do you guys want to be the next scientist who come up with that?
Yeah, I totally got goosebumps. That was super cool.
I know, it's like, it's going to change everything. And that's incredible. And then DeepMind's AI predicts structures for a vast pool. I actually cried the second time I showed it to my mom as well. And, you know, a database of more than 20 model organisms as well. You know, that are, you know, will set to go by the end of the year from 350,000 to 130 million protein structures. Isn't that amazing? This is something that you guys' grandkids maybe could have come up with. Who knows? But this is insane. This is a problem that was solved years before we thought it could ever be possible. This is something that is so amazing. I think that this is something that is just so amazing. We've been stuck on this problem for nearly 50 years. And, you know, a 50-year-old grand challenge. It has occurred decades before many people in the field would have been predicted. It will be exciting to see the many ways in which it will fundamentally change biological research. That's pretty exciting. Right, guys, this advancement decades before. So we're done for today. So today we talked about what AI is, why we need to make AI products, the 3 categories of machine learning, supervised, unsupervised, and reinforcement learning. And that it fundamentally is all about data, data, data. And tomorrow we'll be up for more about deep learning. So unless you have any questions, I will talk to you guys tomorrow. So thanks for powering through for today. Thank you, guys.
Thank you. At what time are you the video is going to be uploaded?
Oh, as soon as this ends, it needs to get uploaded and then processed, and then I'll share them tonight, hopefully after it's finished, the processing of the recording.
Yeah, because I joined late because like my laptop wasn't working.
Okay.
We didn't get the email and stuff. We got it late.
Oh, okay, okay. Well, thank you for letting me know, Kieran. I really appreciate you still coming, and I will be sharing the recording with you guys so, like as soon. So it's all on the link as well, and I'll send you an email as well. But thank you, guys.
Okay, thank you. Bye. Have a great.
Okay.
You have a good
Have a
day.
great day.
Have a good evening.
Bye bye. A cute dog, Alyssa. He's cute.
Thank you. He's always stealing the spotlight.
Oh, that's adorable though.
It's almost 10 p.m. here.
Oh yeah, I know it's also pretty late here too. Sorry for keeping you guys up. Bye bye, guys.
Bye.
Bye.